to be recording this session, I think. Yes, it starts.
Yes.
So it's a pleasure for me to receive Jian Mao today for the presentation of the RQMP. Yes, so Jian did his undergrad at the Huazhong University of Science and Technology in China, and he finished his PhD at the University of Hong Kong in 2018. So since then, he's been a postdoctoral fellow in Prof. Stéphane Kenakowan's group at Polytechnique Montreal. And he is currently researching in large area black phosphorus and perovskite optoelectronic devices. So today he's going to talk to us about black phosphorus, thin films, and photodetectors. So the floor is up to you, Jian.
Okay, thanks all for the introduction. It's my great honor to give this talk today. I'm going to talk about the black phosphor nanosheets, Langmuir-Blodgett thin film, and photodetectors. First, I would like to make an acknowledgement and thank Professor Stephen Kenakowan and group members for the support. And also, I would thank Professor Antonella Badon from University of Montreal for providing us the Langmuir-Blodgett system. And also thank the financial support from NSCRC and Canada Research Chairs. Yeah, it's a wonderful group, Professor Stephen Kenakowan's group. And the contents of this talk is mainly includes 5 parts. First is about, I will give a basic introduction of the 2D materials, and then followed by some background information of black phosphorus. And then we fabricated black phosphorus thin films from nanosheets via the Langmuir-Blodgett assembly technique. And with these thin films, we have fabricated black phosphor photodetectors. The last part is about our ongoing project, that is the defects in black phosphor nanosheets. 2D material is the material in which the atomic organization and the bond strengths along 2 dimensions are much stronger than along a 3rd dimension. For example, within the 2 dimensions, the atoms are formed by covalent bonds, but held together by weak van der Waals force in the 3rd direction. The well-known 2D material is graphene, which was first reported in 2014 by Professor Langmuir-Blodgett and Games from Manchester University. The graphene was fabricated by mechanical exfoliation, also the scotch-tape from graphite that is repeat. Here's the image of the mechanical exfoliation. That repeated peel-off graphite would allow one to achieve even monolayer graphene. And graphene is, even up to now, graphene is very exciting in area, and they have lots of interesting properties. For example, graphene is a semi-metal with 0 bandgap, and the mobility is up to 15,000 square centimeter per volt per second. And also it's free of defects along outer plane because there is no dangling bond. 2D material is a big family, not only graphene, there are also some other 2D material. Different 2D material have different applications. For example, the transitional metal that chalcogenides, such as MOS2, that can be used for transistors and batteries, and also some oxides, such as titanium oxide, that has been reported to show some superconductivity. And some, for example, some other 2D material that is hexagonal boron nitride, which is an insulating material because of its large band gap, that can be used to work as dielectrics of transistors and also UV light emitters because of its band gap is about 6 electron volt. And here we focus on black phosphor because, of course, it's also a 2D material. And besides, its band gap is quite low, about 0.33 electron volt. And it's also tunable from 0.33 to 1.5, that is spanning from visible to infrared region. The application of black phosphor includes such as medical imaging, optical communication, and also night invasion. Black phosphor is the most thermodynamically stable allotrope of elemental phosphorus. It crystallizes in orthorhombic structures, that is within each layer. Each phosphor forms covalence bond with three neighbor atoms, and within each layer they are formed by weak van der Waals force. And there's a armature direction and a zigzag direction. That is the origin of the anisotropic in black phosphor. DFT calculation indicates that black phosphor is direct bandgap material with bandgap tunable from about 0.33 electron volt to 1.5 electron volt. And the conduction band, the minimal, and the valence band maximal locates at the Z point of the first boson. And besides, the effective carrier mass is much smaller in armature direction. That is ZQ in this direction, and on the first boson, this ZQ is much smaller in the armature direction compared with the zigzag direction. That is ZTA here, this direction. This property leads to the anisotropic carrier mobility in black phosphor. And black phosphor has also been fabricated in different electronic devices such as transistors, photodetectors, and light-emitting diodes. In the transistors, black phosphor works as a conducting channel whose conductivity is controlled by the gate voltage. Since black phosphor is P-type material with hole as the majority carriers, a negative gating would induce accumulation of holes in black phosphor, and as a result, the conductivity increase, so the device works as like in on state. To the contrary, for positive gating, here if the gate voltage is positive, that will induce depletion of the holes. As a result, the conductivity decrease, so the device behave like off state. So the ratio of the current as on state and to the off state is the carrier modulation. Black phosphor transistor could reach about 10 times 5 carrier modulation. And then for the black phosphor photodetector, because of its low band gap, a detectivity up to 4 micrometer has been reported at room temperature. This is quite impressive. The principle of black phosphor photodetector is black phosphor first black phosphor absorb light, and the electron at the valence band jump to the conduction band, leading to the formation of electron hole pairs. As a result, the conductivity increase. And if the electron and holes are injected to the conduction band and the valence band of black phosphor, and then recombine within the black phosphor material, and then emit light, so that is the light-emitting diodes. Our group has demonstrated the first black phosphor light-emitting diodes. Mechanical exfoliation is the dominant approach for fabrication of prototype electronic devices. However, this approach is unscalable, and the size is typically limited to tens of micrometers. For example, this is device, the black phosphor photodetector. The area is about 10 to 20 micrometers. So fabrication of large area thin films is essential for practical applications of black phosphorus. Liquid exfoliation offers advantage of preparing large amounts of 2D materials in solution under sonication. For example, they can prepare a few hundred millimeter solutions with nanomaterials. But how simply using the sonication such as ultrasonic bus or chip sonication, but how to fabricate large area thin films with this nanomaterials? And that's what we are gonna, that's the aim of this this talk. That is Langmuir-Blodgett assembly technique. LB technique, assembly technique, is a well-developed technique that has been used to assemble amphiphilic or hydrophobic materials such as fatty acid, graphene, or graphene oxide nanomaterials. The basic setup of LB assembly is a Teflon trough, which is filled with subphase such as water. And there are two movable barriers that is controlled by motors. And after adding the nanomaterial at the surface, its surface tension will be recorded by a microbalance. And if we close the barrier, the nanomaterial will be much closer, and then the nanomaterial can be transferred to substrate. And because black phosphorus is hydrophobic, so it's like it could be assembled by, with the LB technique. Then we have fabricated black phosphorus nanosheet first using the liquid exfoliation. Since NMP organic solvent has been demonstrated as an effective solvent to exfoliate BP. So, and then we use NMP as the solvent to exfoliate BP in ultrasonic baths. Here is the image of obtained BP suspensions. After centrifugation, to remove the unexfoliated large flakes, we get the supernatant, the second vials. And also we have changed the solvent from NMP to chloroform. Since NMP is miscible with water, but chloroform is immiscible with water, which will be discussed later on. And in order to replace the solvent, the supernatant of the second vial is centrifuged again at higher speed in order to get the precipitate. The precipitate was then dispersed in chloroform. So that's how we changed the solvent. And we also added a certain amount of fullerene to the BP solution in chloroform. Since fullerene has been reported to protect black phosphorus from oxidation. First, the black phosphorus was conferred by the Raman spectrum because we have observed the characteristic of the AG1, B2G, and AG2 peaks. And then we start the Langmuir isotopes. In order to get to start the isotope, we have added 5 milliliter solution, each solution to the LB trough. Of course, the water has been used at the subphase, and after compressing the barrier, the trough area will decrease, and the surface pressure was monitored and increased. We have observed that lots of black phosphorus sink into the water when black phosphorus in NMP was added to the water surface. But it didn't happen for BP or BP fullerene mixture in chloroform. And this is also reflected from the surface, the isotope. For example, for BP NMP, after compressing to the minimal area, the surface pressure increased to about 15 milliliters per meter. But for BP in chloroform, the surface pressure increased to more than 30 milliliters per meter. And the surface pressure further increased to more than 60 if the fluorine is added. And based on this isosur, we could start the transfer of the nanomaterial from the water surface to the substrate. And we keep the surface pressure fixed, for example, for BP in NP fixed at around 12 milliliters per meter. For BP in chloroform, about 30 milliliters. So basically for these two, they are around their maximal surface pressure. But for BP in chloroform, we choose around 40 milliliters per meter. So since this from the curve, we can say this is quite sharp. So this is regarded as the solid state of the molar layer. If we go further, the line becomes shallow. So that indicates the molar layer collapse. And then we measure the morphology of the transferred LB thin films. For the BP from NMP, a handful of material were observed. However, this is expected from its low surface pressure, about 12 milliliters per meter. But for BP from chloroform, lots of material were observed, but they formed overlapping stacking. This is not expected for good thin film for device. However, very interesting is that if the fluorine was added to the black phosphor in chloroform, the morphology is quite uniform and homogeneous. And we think this could be understood that NMP is miscible with water, but chloroform is immiscible with water. NMP is an effective solvent to exfoliate BP because there are strong interaction between NMP and black phosphor. And when the black phosphor solution was added to the water surface, the NMP solvent will drag the black phosphor into the water and then sink down to the bottom. But for BP dispersed in chloroform, because chloroform is immiscible with water, and the boiling point is quite low, around 60 degrees. After adding the solution, the chloroform will float at the surface and evaporate very fast. As a result, the black phosphor nanosheet will float at the surface instead of sinking into the water. So that's why we observe lots of material, and also the surface pressure is much higher. However, there is another paper that they use NMP as the solvent. However, we can't reproduce their work. Besides, as you can see, the previous nanosheet is quite small, less than few hundred nanometers. And we have changed the centrifuge speed in order to get some larger flakes. And as you can see, lower speed could lead to black phosphor nanosheets with larger size, more than 1 micrometer flakes observed from the morphology. And that is to say, even larger flakes that could also flow at the water surface and be transferred onto substrate. And in order to investigate the optical property of the black phosphor thin film, we have transferred the black phosphor fluorine thin film from water surface to fuse the silica. And also for comparison, the pure fluorine was also transferred. As you can see, with decreasing the centrifuge speed, the color is dark, a darker color is observed. And besides this, to the best of our knowledge, this is the largest black phosphor thin film has been reported till now. With this thin film on fused silica, we have measured the UV visible near-infrared absorption of the thin films and using integrated spheres. After obtaining the transmittance and the reflectance, we calculate the absorptance. As you can see, the absorptance gradually increase if the centrifuge speed are reduced, since there are more large flakes obtained remains in the thin films. And besides, for the lower centrifugation, absorption up to 2.3 micrometers were observed. And besides, the absorption peak at 340 nanometers exists in all of the thin films. This peak is the characteristic peak of fullerene. So that is to say, in this thin films, there's black phosphor, there's also fullerene. Of course, since we added to the solution. But how does fullerene prevent black phosphor overlapping stacking, and what's their interaction? And Chen and the co-author has observed absorption peak at 1075 nanometer in the mixture of BP and fullerene. And this peak is typically attributed to the fullerene radical anion. So they proposed, so they thought there's an electron transfer from black phosphor to fullerene, and then leads to the formation of phosphor radical cation and fullerene radical anion. However, we didn't observe such peak in the mixture of BP fullerene in chloroform. As you can see, the red curve, there's no such peak. To the contrary, we have observed a strong peak at around 1075 nanometer if the fullerene is dissolved. If fullerene is dissolved in NMP, there's no black phosphor. And besides, and we have observed that the color of fullerene in NMP is brown, but fullerene in chloroform is pink. This is the pink color is the normal color of fullerene. So that is to say, the real mechanism is the electron transfer happens between NMP and fullerene instead of black phosphor and fullerene. And besides, the radical reaction has been reported between fullerene and amines, such as propylene, butylene, and etc. And besides that, the peak gradually increased with time. So we think the reason why Chen only observed very weak peak in BP and fullerene because they didn't dissolve it enough time. But so the peak is very low. Basically, if they increase the time, we think they should also observe peak for the fullerene in NMP, since they use NMP as the solvent. So, and also we have also investigated. We have observed that the peak in BP and fullerene LB film at 340 nanometers disappears after toluene wash. Toluene is a good solvent for fullerene. So this peak, disappear of this peak indicates that the fullerene was removed by the toluene. So that indicates that the most probably BP and fullerene is physical absorption instead of some chemical reaction or something. And with this result, we have proposed under the mechanism how fullerene prevents overlapping stacking. Since black phosphorus is hydrophobic, they tend to overlap at the water surface in order to reduce the contact area. And if the fluorine is added to the black phosphor, the fluorine within black phosphor or on the black phosphor would prevent the overlap when the nanomaterial was compressed, since we need to compress the barrier to make the nanomaterial quite closer. So the fluorine prevents the overlapping. And also we investigated if the black phosphorus is oxidized or not, since we use water at the subface, and the black phosphorus is easily oxidized, especially at the edge and the surface. And then we transfer the black phosphor to the copper grade and measure some flakes. And this is typical flakes. And we did the EDS. As you can see, there's no peak at 0.5 kilo-electron volt, which is the peak of oxygen. So the oxidation is negligible. And besides, the discrete peaks from the fast Fourier transform of the high resolution TEM indicate that the flake indicates the crystallinity of the black phosphorus flakes. And with this homogeneous thin films and absorption from visible to near infrared, and also negligible oxidation, we have fabricated black phosphor photodetectors. The photodetector is basically a two-terminal vertical structure, that is ITO and silver work at the electrode, and zinc oxide and TAPC at the electron transporting material and hole transporting material. And here is the real device, about 4 millimeters. And to the best of our knowledge, this is also the largest black phosphor photodetector. And we characterize the photodetectors, and after measuring the current under dark and illumination of laser at 660 nanometer and 808 nanometers. As you can see, the current increase after increasing the light, the 660 nanometers. And besides, there is a shift of the current minimum from 0 to about 0.225 or something. So this is the photovoltaic effect due to the formation of quasi-Fermi level in the device. And with this IV curve, we have calculated the responsivity. That is the light current minus the dark current divided by the input optical power. And the obtained responsivity is in the range of milliamp per watt. This value is comparable with reported black phosphor from liquid exfoliation in literature. So the conclusion is that large area black phosphor were fabricated via Langmuir-Blodgett assembly technique, and the fluorine prevents black phosphor from oxidation and also overlapping stacking during assembly due to a physical absorption. And also we have demonstrated the first millimeter scale black phosphor photodetectors, which shows responsible from visible to near infrared. Another project is the defect in black phosphor from liquid exfoliation. And there's a question that has not been answered. That is why the absorption of black phosphor from liquid exfoliation is so low at the infrared region. For example, from the BP, if the BP was fabricated from from high centrifuge speed, the absorption at this area is very low. And if we do the tau plot in this area, so the band gap looks like in the visible region. And not only we have observed this phenomenon, it was also reported in literature, and it's not explained why. Since normally a black phosphor nanoflake, if it's more than 5 nanometer, it should behave like a bulk. For bulk, black phosphor is direct bandgap material. The absorption in the infrared should quite high, even if there are some monolayer or bilayer black phosphor, but we didn't observe the absorption edge in this area. So this question has not been answered, has not been understood and not answered. And if we compare with the mechanical exfoliated BP, for example, clearly a absorption edge could be observed, and the absorption in this area is quite high. And also from the simulation, the absorption is also much higher than what we have observed from the liquid exfoliation. So to understand that question, we have measured the TEM of the black phosphor nanoflakes from liquid exfoliation. And here is the selected area electron diffraction of the flake, typical flake. And here we have investigated 3 spots, 1, 2, 3. And from the spot 1, and there are clear 2 spots that strong spots were observed. That is, there are 2 and 2 there are plane. With this 2 peaks, we could decide that this flake is in the 0, 1, 0 zone axis. But for spot 2, you can say the 101 peak increase, and is quite comparable with 200 or 002. And for the spot 3, the 101 peak is much stronger. However, the plane 101 plane should be systematically absent in bulk BP. Why? Because, and we can understand from the structure. For example, the black line is the 101 plane. So this is the 101 plane, and we can understand from the Bragg's law. Here, this 2 plane is the 101, and at a certain angle, the ray 1 and the ray 2 will satisfy the Bragg's law, so we could observe the diffraction peak. But if there is another plane lamps right in the middle, that is, this plane would cancel the diffraction peak. Since we can say between the 101 plane, there is another plane that here, this would cancel the diffraction peak. So that is to say, we shouldn't observe 101 plane in bulk black phosphor, but we observed in the selected area diffraction peak. Why? And besides, the 101 plane was also observed in literature for BP. The BP was also fabricated via liquid exfoliation. And this plane was attributed to a monolayer, since they have calculated that, for example, the ratio of 101 to 200 is very very small for black phosphor if the layer is more than one layer, that is more than one monolayer. For bulk, the value should be very small. The value only increase, that is when black phosphor is monolayer. However, the 101 plane was also observed in flake that is more than 3 nanometer. More than 3 nanometer, that indicates the black phosphor has around 6 layers. So they conflict with each other. And for our case, for the spot 3, this is definitely more than 1 layer. Since we can say for the spot 2 is lighter, this may be 1 or 2 layer, but for spot 3, this is definitely more than 1 layer. And recently, we found that DFT found a work that they use DFT calculation and they found that there might be a delta state that is a stacking fault that might exist in black phosphor. This stacking fault happens when black phosphor, for example, AB is a typical black arrangement of black phosphor, and if the second layer shift along shift at 0.28 times A, 0.5 B, and shift it to the A delta, and this state is metal stable, and it could also exist. And this state, the energy barrier from AB stacking to the A delta stacking is 14 electron volt per unit cell. So that is this state could happen. Especially more important, the band gap of the A delta stacking is larger and it becomes indirect. For example, you can say this is the AB stacking, and if for the A delta stacking, the conduction band minimal and the valence band maximal is not at the same and is not at the tau gamma point, and this is very interesting. And based on this calculation, we have did the selected area electron diffraction simulation. For bulk, we can only see the 002 or 200 peak. That is what we have observed from the experiment, from the spot 1. But for more monolayer, we can say some 101 plane. This is also in agreement with the literature. But if we when we simulate the A delta stacking, the 101 plane could be observed, since the there's no such plane length located between 101 plane. So we think the stacking fault might be the origin of the 101 plane, and also explain the abnormal absorption of black phosphor from liquid exfoliation, because the stacking fault increased the band gap and also changed the direct band gap into indirect. For the future work, we think scalable approach to fabricate high quality, large area black phosphor is very important, since at the moment, there's no approach that could achieve this target. But this is important for real application of black phosphor. And also black phosphor is easily oxidized, so how to protect and also encapsulation of black phosphor is also important. Okay, thank you so much.
Thank you, Jian. Do we have any questions from the audience? Can you raise your hand or? Okay, so perhaps I will just start with my question. So as far as I know, black phosphorus has some problem with oxidation with water and light, right?
Yeah.
So I thought that was the main challenge with black phosphorus, and then you have to encapsulate it and everything.
Yeah.
But here you talked about the fullerene. So is this kind of a solution to this problem? Or did I understand correctly that fullerene can make it less oxidized and like more stable in the end?
Yeah, first fullerene has been reported to protect the black phosphor since fullerene is hydrophobic. And also from our result from the TEM, the EDS of the TEM. At the beginning, we don't know if there is oxidation or not. And after from the EDS result, seems the oxygen signal is negligible. So we think the fullerene could work prevent the oxidation.
Completely or partially? Because you still have to.
I think at least partially.
Okay.
Not completely. And also it depends on how it's covered, how the fullerene is covered. If it's covered very good, I think the protection is quite good.
Okay, that's very interesting. Michel, you have a question?
Okay, thank you for the nice presentations. I had a question about you. The calculation shows that the gap should be indirect for your delta, for your, how you call it, your delta alpha.
Yeah, a delta
terms.
Yeah.
Do you have any experimental evidence of this indirect nature of the band gap?
No, we don't have the we don't have direct experimental evidence. We just since we from the absorption spectrum, especially for the flake that is produced from higher centrifuge, the absorption curve is a bit strange. It doesn't behave like a direct bandgap material. Okay, that's not that. It doesn't agree with the measured black phosphor from mechanical exfoliation. The absorption, whose absorption is quite high in the infrared region, and it also doesn't agree with the simulated absorption spectrum. So we think this is kind of possible evidence of the black phosphor is a indirect bandgap material after change from AB stacking to A theta stacking.
And one way would be to look at the photoluminescence, and usually indirect system don't have much photoluminescence. So were you able to observe photoluminescence of that, or?
No, yeah, that's good. That's good question. And we have tried to measure the photoluminescence of black phosphor from liquid exfoliation, but we didn't observe any signal.
Okay.
And but for the mechanically exfoliated BP, and we could easily observe the photoluminescence.
Okay. So as far as I understand, you're saying that you so that the liquid exfoliation seems to be not monolayer but a bilayer with a default stacking in it. So is that your conclusion out of that?
Yeah, or? Yeah. We think after the liquid exfoliation, there might be some stacking fault, especially since the black phosphor, the interlayers, I mean the force between each layer is van der Waals force is quite weak, and that's possible. There's possibility of shift of the different layer under the force of the ultrasonic bus or tip sonicator.
Mm-hmm. Okay, but when I look at the calculation that you have shown here on this page, page 32.
Okay, third.
Okay, so there's not that much a difference between the 2A, well, the 2-layer systems and the 2-layer delta system here in terms of the value of the gap.
The gap is not too much, but you can say there's around 4. This is
1 and
yeah, maybe 0.3 or electron volt or something, but it becomes indirect, so there needs some phonon that will contribute to the absorption.
Can you show again your absorption or your data?
Okay. The left one is what we have measured for the black phosphorus thin film, and the middle one is what reported from the liquid exfoliation in solution.
Okay. And the next graph, I thought you had like a. Oh yeah, that was example, here what you showed that this was the anomalous.
This is mechanically exfoliate and the absorption in the, for example, the third graph. Yeah, this is quite strong, and they have the absorption edge. That is direct bandgap material, and from the calculation, the BSE calculation, they could also clearly see the absorption edge, and the absorption is strong.
So you relate the mechanical one to D here, like a, because one is in wave number, like a micrometer, so you have to read it.
Yeah.
The other one is in EV, is that?
Yeah, this is EV. EV2, so 1, okay.
So you have a, like a, as far as I understand now, your black phosphorus, like which is on column E, this is not a monolayer, this is like a bulk system?
Yeah, for the D is bulk. So since exfoliate BP, we think it's it depends on the centrifuge speed. If its centrifuge is not very high, most of them should be at least a few nanometer. So more than 4 to 5 nanometer, it should behave like bulk.
Okay.
And also from this PL spectrum, you can say even 4.5 nanometer, the bandgap should be more than around 3 micrometers. So they are quite close to the bulk.
This is luminescence?
Yeah, this is the photoluminescence.
Okay. So you're saying as soon as you get to 10 nanometers or even, yeah, wow.
Yeah, if it's 10 nanometers, of course it's bulk.
It behaves like balls.
Yeah, behave like bulk.
Yeah. And if you go back to the next one you have, and so here you see a difference between 49, 350, and 1,000. So, but the gap remains the same. It's just the intensity of the absorptions.
Yeah, exactly.
Okay. Whereas your samples, they're not here, huh?
No, not here. We didn't measure the the pure of mechanically exfoliated BP. This is reported.
All right. Okay. Thank you.
Okay. Thank you.
Any other question? So maybe I have another naive one on the chemistry, maybe a little bit. So I'm just wondering, so you have your black phosphorus and then you put it in NMP and fullerene, and you see that NMP and fullerene kind of exchange electron and they become radicals?
Yeah, actually, we conclude that the electron transfer happens from NMP to fullerene instead of black phosphorus to fullerene. Since, for example, from the green line, we simply dissolve the fullerene in NMP, we could observe the the peak.
Mm-hmm.
So
my question, I guess, is now that you've introduced radicals, isn't that like, to me, it's kind of bad for the stability of the material if you have radicals floating around. So
yeah, this is not good. But we didn't. We use the chloroform and the solvent later on.
Okay.
We only use NMP to liquid exfoliate the BP and then change to chloroform. And not only NMP is not good for the LB sampling, but it's also not good for the stability. There's a radical chemical reaction.
Okay, I see. Okay, thank you very much.
Thank you.
Do we have another question? We still have a little bit of time. So if not, join me to thank the speaker again. Thank you, Jian, for the very interesting talk. And we see you next week for Prof. Audrey Laverdure's talk, same times in 1 week. Thank you, everybody.
Okay.
Have a good week.